So hello, everybody, and welcome to today's IQIM seminar. Today we have Ran Finkelstein, who's a postdoc with Manuel Endres at Caltech, working on neutral trapped atoms. He's a Troesh postdoctoral fellow. Ran comes from finishing his PhD at the Weizmann Institute of Science, where he worked with Professor Ofer Furstenberg, developing schemes for strong light-matter interactions in inhomogeneously broadened warm atomic vapors for quantum nonlinear optics. And I believe that's the topic of his talk today. So I give you the floor, Ran. Also, I just want to encourage people, as the talk progresses, feel free to raise your hand and ask questions.
Okay, thanks a lot, Andre, for the introduction, the opportunity to speak here. So does everyone see my screen and my pointer?
Yep, we do.
Yeah. Okay, great. So so indeed today I want to tell you mostly about my PhD work coming from the Weizmann Institute about coherent light matter interfaces between photons and highly excited thermal atoms. So the stars of today's talk are going to be these photons, and these photons will be living, like the rest of us, actually in a hot and noisy, inhomogeneously broadened material world. This is always the case that it doesn't go. Okay. Yeah, so why work with hot atoms? We usually, when we think about quantum things, we think about ultra cold things. So one motivation is that this is a technologically proven scalable system, such as already proven by so-called first-generation quantum technologies, such as miniature atomic clocks and magnetometers, but also was used, for example, for distributing entanglement between remote atomic nodes. The question is, can we take this step forward by realizing strong light matter interfaces, just as realized with waveguides and resonators on chip here, or even by realizing localized material qubits, such as proposed here by Tilman Faum from Stuttgart, by channeling micro vapor cells connected by glass waveguides. So to set the scene for everything that I want to present you today, let's start from a schematic description of such a coherent light matter interface. This will be composed from a focused Gaussian beam and a glass cell containing atomic vapor. Now, if we'd like to encode, extract, or measure information in such an ensemble, it's typically instructive to consider collective excitations. So for example, a photonic number qubit can be encoded in the basis spanned by the collective ground state, or all atoms being in this black state, and a single delocalized yellowish excitation. This yellowish excitation is created by a photon absorbed here, here, or here. And in general, we say that, of course, it's a coherent superposition of all of the above options. And this coherent superposition has a phase relation with the excitation wavelengths denoted by this wave vector K. Now, what is this internal degree of freedom? It could be a nuclear or electronic spin, as usually people use in these so-called lambda type systems. And this is why these systems are sometimes, or this collective excitation is sometimes known as spin waves. But at least throughout my PhD, we've mostly focused on these orbital excitations, which were historically less studied because of some understandable reason, some shorter radiative decay times and larger inhomogeneous dephasing. But as I hope to show you, they also carry some great advantages. So I'd like to review several typical length scales of the problem. So first of all, we said we have this collective excitation. So this has equal probability of finding the excited atoms throughout the ensemble, but this has some varying phase. So the typical length scale over which this phase will vary by 2 pi is the excitation wavelength. Then we also have the beam size, W0, and the length over which we can maintain this size, which is the Rayleigh range. We have the attenuation length, or the length over which the electric field of the photon will decay to 1/e as it goes through the atomic ensemble. And this really quantifies the strength of light to matter interactions, or with what fidelity can we make these mappings. And this is sometimes also known as the optical depth of the ensemble. Now, if these atoms will be interacting through some dipolar or van der Waals interaction, then we should also consider the length scale over which these interactions dominate. Now, since this is a thermal ensemble, it has a Maxwell-Boltzmann distribution of velocities with typical velocity Vt, these length scales would translate to typical time scales. So for example, atoms moving through this excitation wavelength with random velocities v drawn from this massive Boson distribution would pick up random phases. And so if we now created this collective state at time 0, and now if we run the dynamics forward, we see that this collective state decoheres for these phases. So this will result in an typical inhomogeneous dephasing time. We can also have transit time of atoms traveling through the beam, and these will be incoherent processes. On the other hand, we can also enjoy coherent processes, such as the delay time of light, of a pulse of light traveling through the medium, which could enable us to then store it and realize a quantum memory. And also phases of photons, which accumulate as they travel through the medium through these dipolar interactions. So the question is, can we do something to stretch these two timescales apart and enjoy the coherent processes while not being overwhelmed by the incoherent processes? And so with that introduction in hand, and I want to show you what our contribution is to the realization of quantum technologies at room temperature, where we try to indeed bridge these length scales apart. And so I'll mostly focus on these two works on quantum memories and how to maintain their coherence. But in the end, I will also briefly show you a new interface we've realized between the evanescent field of a tapered optical fiber and an atomic gas. And so these works will have two main applications at mind. The first are quantum networks, which are meant for generating large correlated states of light. And the second is quantum nonlinear optics, or how can we realize effective interactions between photons as they travel through this atomic medium. And this will be nonlinear at the level of single photons. Okay, before I proceed, I'd just like to point out that this is not only motivated by room temperature quantum technologies, but in fact, almost any quantum platform suffers from some form of inhomogeneous dephasing. So for example, the reason why the Molmer-Sorensen gate is so successful is not because they were the first to suggest a way to efficiently entangle two ions, but they were the first to suggest a way to do that in the presence of residual atomic motion, as you can see here. Neutral atom entanglement, which is why I'm currently studying, is at times also limited by atomic motion. So as you can see, the coherence time of a qubit here in this neutral atom system could be limited by inhomogeneous dephasing. Artificial atoms, such as NV centers and solid-state spin qubits, are also limited by inhomogeneous magnetic fields and inhomogeneous strain. So these are all part of a canonical problem in quantum information processing, which is known as inhomogeneous dephasing. And so the question really is, can we design general schemes to mitigate all of these inhomogeneous dephasing mechanisms, or many of them? And will these general schemes hold in the extreme case of a room temperature gas, as I've shown? Okay, so let's take a step back and discuss what is inhomogeneous dephasing. So inhomogeneous dephasing can be described by this canonical problem of a spatially varying fluctuating field in space or in time. And so in this canonical, say, NMR type problem, each one of these spins in the ensemble would rotate or would precess with a different frequency. And if we now try to average over the mean value of the spin, we see that it decays with a typical time scale T2 star. And if this noise has a Gaussian profile, then this will decay as a Gaussian. Another way to look at it, if you like, is if we look on a two-level system or a qubit, then each copy of this qubit suffers from a different shift delta. And this shift fluctuates from shot to shot of the experiment or from member to member of the ensemble. So typically the solution is, and this has been an amazing workhorse as the advent of NMR and going into quantum information these days, and has many variants, is essentially to flip the arrow of time. So what do I mean by that? If halfway through this coherent evolution, we flip the spin, then we know that each one of members of the ensemble could pick up a equal magnitude opposite phase. And then at the end of the time evolution, we can regain the coherence. Now, as I said, this is, of course, has many variants and is very, very useful, but also has some inherent limitations we can already notice. So for example, we can only regain coherence at specific predefined times and not continuously throughout the evolution. And this means that also in the frequency domain, we can only protect from a specific bandwidth of noises, which will be determined by these times. As we drive the qubit with these strong short pulses, we also induce sensitivity to drive noise of these pulses. And finally, and perhaps more fundamentally for me, the question was, can we always do this trick of flipping the arrow of time? So for example, if we did have this process where atoms are just flying randomly and freely in space, and we don't want to take each one of these atoms and put them back into the original location, can we do something to continuously protect the collective coherence of this state? And so our solution involves identifying a third auxiliary state, which we denote as a sensor state. And this sensor state has enhanced and opposite sensitivity to the same source of inhomogeneity as the qubit. So if this qubit shifts by plus delta, this sensor state transition frequency would shift by minus s delta, s being larger than 1. And so we can see that if we now admix coherently this sensor state with our qubit state, then we only need to admix 1 over the sensitivity factor s to realize a new qubit, which is protected from inhomogeneous dephasing. Now, if we do this with an off-resonant field, we know that this will induce a light shift, it will change the qubit transition frequency, and this would also rotate the phase of the qubit in time. So if you'd like to avoid that, we can introduce 2 fields with equal detunings, 2 symmetric detunings and equal strength. And so this protected qubit now will have the same original transition frequency, so the phase will not rotate in time, and will actually be better protected from this inhomogeneous dephasing. So we can work out the conditions of optimal protection. So what are the relation between the Rabi frequency omega and the detuning delta of this detuned dressing field? And we can do that for a single field, for 2 fields, and actually for any number of fields. And for example, you can see that for a small sensitivity factor S, the resources we need with 2 dressing fields are smaller. And so we say that the 2 dressing fields do not introduce any energy shift. They protect from the original sigma z noise, and they also protect from any sigma x noise in the driving fields. Okay, any questions so far? Okay,
is it a strict requirement that the sensitivity of the excited state has to have the opposite sign?
It is somewhat of a strict requirement. It's actually the natural choice. So if this third state would have a lower sensitivity, you would probably choose to encode your qubit on this state to begin with, and then this will be your sensor state. Right? But generally, you would pick your qubit by the qubit that has the least sensitivity to any perturbation, but still always typically has some residual sensitivity. And then you can always find some other state which has a larger sensitivity.
Okay, thank you.
But in fact, the new qubit will be some J state of both of these levels. So at some point, if the sensitivity is not too large, it's kind of hard to say in the qubit which state is which. Okay, so
actually,
yeah,
I have a question.
Yeah.
So does this scheme actually only work for a large delta regime where delta is much larger?
It significantly benefits from large detuning. So we show how it scales with detuning, but essentially, you're right, it benefits from large detuning. So essentially, we'll attenuate the noise. For a single dressing field, we attenuate it as 1 over delta. And as with 2 fields, we attenuate as 1 over delta squared.
Because in the plot you just showed, in the plot you just showed, like it seems like it also works when omega is comparable to delta, where you actually drive, population to this S state. So you just showed like one curve, I think.
Yes.
So you like show maybe this plot again.
Yeah. So you're right.
In this plot, basically, if I read off the number, so I was wondering whether it works for like this kind of driven case, basically, where you populate a little bit of population in the S state.
Yeah, so in this case,
because when omega is comparable to delta, then you will populate, right?
You're right. Yeah, you're completely right. So the amount of dressing grows as omega over delta grows, and so that means that you also populate this sensor state. And so the question here is, does this sensor state has any additional decay mechanism? Then you will also introduce the decay mechanism of the sensor state into your qubit. And if it does not, then you can still coherently admix this state into your qubit. And in the end of the time evolution, you can adiabatically ramp down this dressing field and map all of the population back to the original qubit state. And then essentially you end up in the same state. Okay. And okay, and to show you one application where this is, for example, useful, so we can consider, let's switch gears for a second and consider quantum optical memories. So quantum optical memories are these reversible and coherent light-to-matter interfaces. In atomic ensembles, these are usually realized by this canonical lambda type systems, which is called lambda because it has the shape of the letter lambda. And here the signal field can be a very weak field. It can be a single photon or a photon qubit. And the control field would be a very large classical fields. And we use these two fields to couple these two spin states through this short-lived intermediate state. And so if we send a single photon into the ensemble and we ramp down the control field, if we do this adiabatically, we can map the electromagnetic field into this collective excitation. And this will be a coherent mapping, which would maintain the phase of the original field, its direction, polarization, and so on. This is, of course, very well known and has two main use cases. One of them, if you have a very long coherence time, you can use this to realize a quantum repeater or quantum communication. But it turns out even if this, and then you can, of course, read out this atomic ensemble by applying again the control field and using the phase matched emission, much like in a phased array radar. But it turns out that even if you have short-lived memory, you can still use this memory to perform local operations on your quantum network. For example, to realize local synchronization of probabilistic single photon sources. So here, let's imagine the following application where we have many probabilistic single photon sources and we want to get an n photon click at the output. Then we would charge one of these memories and wait until we get a herald on all of the other memories being charged. And then we can release, given that all these memories are still coherent and alive, we can release an n photon click at once. And so here, the parameters which will govern the performance of this kind of memory is not just the coherence time of the memory, it's actually what's called the effective fractional delay. So this will be the coherence time divided by the shortest pulse width that we can squeeze in our system. So this is sometimes also known as the time bandwidth product, and multiplied by the overall external efficiency of the system. So this, when, for example, for the task of this local synchronization, the rate will be exponential in this figure of merit. Okay, so what's the problem with current realizations? What's the problem with lambda systems? So lambda systems are inherently slow. They're actually, to couple both of these spins, for example, in a hyperfine manifold, we need to use the hyperfine interaction, as light only couples directly to the orbital degree of freedom. And hyperfine interactions are inherently slow. So for example, here in this rubidium vapor, they're on the order of gigahertz. So we cannot perform this operation with a bandwidth larger than a gigahertz. These lambda systems are also inherently noisy. So there is always some crosstalk between the control field and the populated transition, which will generate four-wave mixing or through spontaneous Raman scattering. So if this control field would couple to this, slightly coupled to this level with spontaneous emission, we could generate a spurious spin wave or a spurious excitation, even if we had no single photon at the input of the memory. So with no photons, we can still get photons, and this will, of course, affect our fidelity. Okay, a solution that we propose is to invert the scheme and to go from a lambda type system to a ladder type system, where we store the photon on the coherence between two orbitals rather than two spins. So in this case, it will be the s orbital and the d orbital in rubidium vapor. And this scheme has several advantages. First of all, it can be arbitrarily fast, since now we only couple to orbital degrees of freedom. We don't need to flip a spin. We don't need to flip a spin. That means we are now only limited by the atomic shell separation and not by the hyperfine interaction. This is also inherently noise-free, as there could be no process that would cause spontaneous absorption to this doubly excited state. And we can extend this scheme to couple into even higher lying orbitals, known as Rydberg orbitals. However, since the wavelength of these two-photon process will be different, then we will have a special varying phase across the ensemble. And this means that we'll suffer from fast motional dephasing as atoms will move through this phase. Okay, so how do you actually realize this in experiments? So we have an atomic vapor cell. We send a signal pulse and a well-timed control pulse. If you do just spectroscopy of the system, you can see we have a single photon transition broadened by Doppler. And we actually have a good resonator, a good narrow absorption line, which has small residual Doppler broadening due to the fact that these fields are counterpropagating. And the process at which we store or we map the electromagnetic field onto atomic coherence can be heuristically visualized as the control field light shifting the transition, dressing it, broadening it to accommodate the full bandwidth of the pulse, and then adiabatically converting it into a dark state. And so the fast time varying field actually breaks this time bandwidth product. So we can store very broadband photons for a long coherence time. So yeah, we ramp the control field down, we wait in the dark for a while, and then we turn on only the control field, and we see that all the atoms emit the signal photons in a phase match direction to the single mode fiber to the detector. And if we repeat the experiment many, many times, we can gather the statistics of what is the probability to get a photon out after a certain wait time. And we can plot this, and we see actually an interesting phenomenon to start with, which are these quantum beats. So where do these quantum beats come from? So they actually are an inherent part of our broadband and coherent nature of our memory. So if we consider the full Zeeman and hyperfine manifold of this atom, then if we have a very broadband photon, it actually couples to several intermediate states, and then it is coherently stored onto several of these doubly excited states. And so when we try to read off or to convert the atomic excitation back to photons, we actually get a coherent beating, which is in the frequency of this hyperfine splitting of the 5 theta, as can be seen in this spectroscopy. This is quite interesting, but maybe not a very good quantum memory if we have these holes in the middle. So if we now actually optically pump all the atoms to the maximally stretched state, then we transform this complicated multi-level atom into actually a clean 3-level atom, and then we see that we have this smooth decay. Okay, and so in this realization, the memory lifetime, this 100 nanosecond, is currently limited by residual motion, as we said. So we have some residual wavelength, excitation wavelength of 150 micron, and the D state, which is still quite a low-lying state, so it still only lives for a couple hundreds of nanoseconds. So of course, if you go to higher-lying states, they will live longer. Still, even with this relatively short time, as we said, what we care about is not the coherence time of the memory, but rather the coherence time of the memory times the bandwidth of the memory times the external efficiency. So if you multiply all of this and you consider the task of synchronizing these 6 probabilistic single photon sources, we can see that this realization does quite well compared to other memories realized, both in terms of this time bandwidth product, or the rate of 6 photon events, and in terms of how much noise we add, or how much do we contaminate this single photon state. Okay, and this was actually also realized by Ian Wemslich's group in Oxford, and is now the basis of a new quantum startup company, which is known as Oracle Computing. Okay, let me come back to motional dephasing. So can we do something to elongate the coherence time of this memory, and in general to fight motional dephasing? So let's have a better description of this motional dephasing. So as we said, we map a single photon state into this W state of this collective excitation. And this has the phase of the 2-photon transition. And now if we just wait, we can see that atoms move to random positions or pick up random velocities k, v, j. And one way to think about this is that the W state is being rotated into a dark state, which is no longer coupled to the ground state. So the energy is still there, but it has completely dephased. So we can already see that this very much looks like an inhomogeneous dephasing problem. And so when we try to read out the memory, we see that we can actually quantify the collective coherence of the state by looking at the memory efficiency. And this will decay as a Gaussian due to the motional dephasing and also as an exponential due to radiative decay. So motional dephasing is indeed inhomogeneous dephasing. I'd like to point out that this is also a limit to neutral atom entangling gates. So for neutral atoms, if we entangle them, we also pick up the phases of these of the laser exciting the atoms into the Rydberg state. And now, if these atoms have some residual motion, then in every shot of the experiment, they will pick up a different random phase. Okay, so how to protect this memory from motional dephasing? So as we said, we identify a third sensor state, which has enhanced and opposite sensitivity to this motional dephasing. So we identify a state which is also sensitive to these velocities Vj. And in this case, this will actually be a high-line Rydberg state. And so while this qubit has a relatively long wavelength or a low sensitivity to velocity, this single photon transition, which has a micron wavelength, has very large sensitivity to velocity. And so if we mix these two together with the right conditions, we can find a state which has less sensitivity to velocities. How would this work? We initialize the atoms at this collective excitation, and then atoms move. So with no dressing fields, if we now look not on position map, we look on this position velocity correlations, we can see that atoms with fast positive velocity move to the right, atoms with negative fast velocity move to the left. But if we average over each and every position, our average coherence or average phase decays to 0. If we now introduce a single dressing field, we can see that we can protect the phase, so we can maintain the phase of all atoms up to second order in velocity. So if we now sum over this position, we still have some coherence, but actually we see the light shift effect as we get a global phase shift of this spin wave relative to the original phase spin wave. If we introduce two dressing fields with opposite and symmetric detunings, we can protect better, so up to third order in velocity, and we also have no global phase shift. Okay. And the way to visualize this, and this maybe has to do with what Juni asked, so you can think about how can you gain? So you can gain by going to larger and larger detunings. Then you can approximate this velocity-dependent light shift introduced by the dressing field. And you can work this out in orders, and you can see that if we have a single dressing field, then we are sensitive to second order in velocity. So we have velocity squared over the detuning to the third. But with two dressing fields, we also get rid of this term. Okay? But this is just an approximate solution for large detunings. It actually works also for detunings going to 0. If you think about this more in the dress state picture. Okay. So if we now repeat the experiment and we quantify this collective coherence by looking at this efficiency of getting a photon out with a specific wait time, then we can see in this semi-log plot that if we do nothing, we get a Gaussian decay. With a single dressing field, we can do slightly better. And with two dressing fields, we can elongate the coherence time of the system. And in fact, this realization, we are only limited by the radiative decay denoted by this dashed line here. So if we normalize this radiative decay out, we can see that the inhomogeneous lifetime or dephasing time of the system is much elongated. And we can see how this depends on detuning and Rabi frequency. So again, for each detuning that we choose for the dressing fields, we need to match the Rabi frequency. For growing detuning, we need a growing Rabi frequency. But you can see we do better and better, and we detune further and further and sort of enlarge the capture range of velocities that we protect, or the bandwidth of noises that we protect against. And so this is mostly here limited by this third order correction for the double dressing case. You can also ask, what about the phase? So if we encoded a photonomic qubit on the phase between the collective ground state and the W state, is this phase maintained? So we measure that by putting the memory interferometer and beating pulses that were stored in the memory and retrieved from the memory with pulses in a different frequency, which were stored in a fiber delay loop and then beat with the retrieved photons. And we can see that indeed we get these interference fringes both in for the stored photon and for the retrieved photon, meaning that the memory is indeed coherent. But if we use only a single addressing field, we can see that the phase depends on the Rabi frequency. So it indeed goes as omega squared over delta, which means that there is some sensitivity to noise in this Rabi frequency. But with two addressing fields, to our best experimental certainty, there is no phase shift on the retrieved photon. Okay, so a short recap, and I'll be happy to take questions. So we've introduced a general scheme for continuous and robust protection from inhomogeneous dephasing. This scheme utilizes sensor transitions with high sensitivity to dephasing, and we actually use these bad transitions to protect the qubits. And so I'd like to introduce this system here and ask if you have a system which has some inhomogeneous dephasing, perhaps we can identify together sensor states and identify schemes to protect the qubit from this inhomogeneous dephasing. So we've already collaborated with several groups. For example, in this Stefan Willich group from Basel, they have this single ion clock transition. And this clock transition has some residual sensitivity to magnetic fields due to different lambda G factors. And so we found that if we admix this ground state with the opposite spin using two RF fields, we can actually narrow down the absorption spectrum and enhance the clock coherence.
Can I ask something related to that? So in this case, does your sensor state also have to be a clock state, or can it have linear sensitivity?
It can have, so actually in this case, the clock state also has linear sensitivity to magnetic field. And this state also has linear sensitivity to magnetic field. Essentially, you don't need the sensitivity to be, you just need to have correlated noise between your qubit or clock state and your auxiliary state.
Oh, I see. So in this case, you're still canceling motional effects, or now
no, this is magnetic effect here.
Okay.
But the fact that I'm just saying that this qubit, this clock transition has first order sensitivity to magnetic field because of the different lambda G factors between this s orbital and the d orbital.
I see.
You are right that if this would only have second order sensitivity to magnetic fields, then this scheme would not work in this case, but perhaps a variant of this scheme will.
Okay, thank you.
Okay, next, very briefly, in a couple of minutes I have left, I'd like to show you some other protection from inhomogeneous dephasing in spectroscopy experiments, and also our interacting memory proposal. So far I've shown you protection from inhomogeneous dephasing during a memory sequence, which is akin to a Ramsey sequence or to free induction decay in NMR. But actually, you can use similar ideas to protect platforms which suffer from dephasing during drive. So this will be akin to CW spectroscopy or Rabi spectroscopy. And for example, for inhomogeneously broadened media, this dephasing during the drive reduces the absorption cross-section of the atom. So it really reduces the strength of the light and matter interaction. So this, for example, this inhomogeneously broadened Doppler line is not only more broad, it's also attenuated, so it has a smaller absorption cross-section. And I'll just briefly mention that if we introduce now similar recovery or protection fields during spectroscopy, we can both narrow down the lines, but also enhance the absorption cross-section. So this is not only Doppler-free, this is actually Doppler-compensated. So we really take atoms which did not absorb resonantly in this and actually harness all of the atoms to absorb together the same resonance transition. Okay, very briefly, we can actually harness now high-line Rydberg states to introduce some interactions into this memory. And in this case, we'd like to harness a special Forster-enhanced resonant case, so we can access these P Rydberg states due to the fact that we have this 3-photon transition. And it turns out that 38P has an exceptionally large C6 coefficient due to these Forster resonances that come from this accidental resonance of two of the atoms, one of them emitting a photon and decaying, the other one absorbing the photon and getting excited. So this is usually an off-resonant process, but for this 38p level, it's nearly resonant. And so we can have strong dipolar interactions between these neighboring atoms. And we can use this to turn classical light or coherent state that we store and read out of the memory into quantum light or light with sub-Poissonian statistics. And okay, I don't want to go very deeply into this, but just to show you that we can realize this either by continuously dressing the memory with feedback excitation or by driving very fast Rabi pulses with a Raman fiber amplifier to a Rydberg state and mapping them back down to the qubit state. And we can already see initial preliminary results with the fact that the light coming out of this memory is now Poissonian, not classical. Okay, and finally, I'd just like to show you in a couple of minutes our recent realization in a completely different direction of interfacing atoms with evanescent field of waveguides. So as I've shown you, we can overcome motion through this excitation wavelength. We can also enhance the interaction strength or shorten this attenuation length of photons going through the medium. But we are still somewhat limited by the fact that we, to get very strong dipolar interactions, we need to focus the light down to match the length scale of these dipolar interactions. And so we can only do that over a limited Rayleigh range. So what if we could squish this Gaussian beam or squeeze this mode to have a very tightly focused beam, which we can maintain over a very long distance? Then we can enjoy interacting with many more atoms or having much larger optical depth. So can this be done? Can we beat the Rayleigh range? So indeed, we know that waveguides, for example, beat the Rayleigh range because they can guide these self-similar modes over distance which can be thousands of wavelengths. But to interface these waveguides with atoms, we actually needed to play some tricks. So this was done in collaboration with Arno Wasserbottom in Berlin. And so here you can see that the mode field diameter and the amount of power residing outside of a core of a glass waveguide, so in the vacuum, free to interact with atoms, as a function of the fiber diameter in units of wavelength in matter. Okay, so as you can see, as long as the fiber diameter is larger than the wavelength, most of the light is contained inside the core. We can get up to 50% of the energy in the evanescent field. And as we taper down the fiber to lower and lower diameters, we get a more and more tightly confined fields. However, at some point, this core cannot support the mode anymore, and we get a very strong divergence of the mode field diameter with more than 99% of the energy residing now outside the core. However, theoretically, there is always a bound solution. This is much like a 1D particle in a box problem with finite potential. So theoretically, there is always a bound solution. The question is, can we reach this point of the fiber diameter being a quarter of the wavelength with 99% of the energy residing outside the core and extending over many, many wavelengths? So this is quite different than the common situation of an evanescent field which decays over a single wavelength. To reach this state adiabatically, we need to taper down an optical fiber adiabatically. And I will not go into how we do that exactly, but the results are that if we now immerse this tapered optical fiber into atomic media, we can see that we can saturate a two-level system with very low pro power. So we get a saturation power of tens of nanowatt, already indicating we have very strong light matter interface. And if we do some time resolved spectroscopy, we can actually monitor. So if we start by pumping the atoms to the excited state by working above the saturation intensity, and then we very quickly, over less than a nanosecond, ramp down to an intensity which is much lower than the saturation intensity. This is indicated by this dashed line. Then we can see how the absorption cross-section of atoms recovers as fresh atoms come into the mode and pop atoms leave it. And we can see that this actually recovers over tens of nanoseconds. Which is already indicates that the mode field diameter is 10 wavelengths and not a single wavelength. So this is already an order of magnitude improvement over previous evanescent field realizations. If we now send two beams, two fields through this tapered optical fiber, so both the probe beam and the control beam, we can see that we have these EAT features, which are quite narrow. So we can have some preliminary evidence to the fact that we can drive coherent two-photon processes in these evanescent fields as atoms fly through it. Okay, with that, I'd like to summarize and take any more questions. And I'd just like to, okay, so in each one of the directions I've shown you, we're now, or the people working on this are now pushing a new frontier. So from tapered fibers to fiber cavities, from coherent, from storage of coherent states to storage of squeeze states and journey to non-classical lights. And towards single readable qubits in these microcells. So you can see these new vapor cells have a width which is around 1 optical wavelength, which gives rise to these interference fringes. So I'd like to take all the people working on this project and show you some beautiful views from Israel, and especially thank my advisors, Ofer, Fristenberg, and Broadband. And I'll be happy to take more questions.
Thanks a lot for the talk. I'm actually going to hand over to Chris if he's online to handle the questions. I'm going to have to run.
Yeah. Yep, here I am.
Perfect. Thanks a lot, Chris. Thank you again for the talk, Ran.
Sure.
So normally I would personally, I actually just missed the last 10 minutes. So
yeah.
I'm.
Yeah, it's perfectly fine. So I think if there are no further questions, thank everyone for listening.
Yeah, let's thank our speaker. Thank you. And if anyone else would like to